Okay, so we are asked to solve the inequality x over x squared plus 4x minus 5 plus 3 over x squared minus 25 less than 2x over x squared minus 6x plus 5. Okay, so this is a rational inequality, and the way to solve, first thing to do when we solve rational inequalities is to rewrite the inequality so we have 0 on one side of the inequality and the rational expression on the other side. Okay, so the easiest way is that to subtract off the 2x over x squared minus 6x plus 5 on both sides to get the equivalent inequality x over x squared plus 4x minus 5 plus 3 over x squared minus 25 minus 2x over x squared minus 6x plus 5 less than 0. So that's the equivalent inequality. All right, now, so we can identify the critical values that make the rational expression undefined. In other words, our related rational expression, r of x, this whole quantity there, undefined, we probably want to factor the denominator. So I'm going to rewrite this here as x over x minus 1 times x plus 5. That's how x squared plus 4x minus 5 factors. And then 3 over, well, we had x squared minus 25, so that's a difference of squares. So that's x minus 5 times x plus 5. And minus 2x over x squared minus 6x plus 5, but that factors as x minus 1 times x minus 5 less than 0. Okay, so we have 3 distinct factors in each denominator, x minus 1, x plus 5, and x minus 5. And so we could see based on those factors, x minus 1 implies that x equal to 1. It makes the rational function undefined. And then x minus 5 equal to 0 implies that x equals 5 is a bad value that makes the rational expression undefined. And x plus 5, which tells us that equal to 0, tells us that x equal to negative 5 will make our rational expression undefined. So r of x, the related rational function, is undefined at x equal to 1, 5, and negative 5. Okay, so next step is to find the zeros of the rational function. So r of x equals 0. All right, so we have x over x minus 1 times x plus 5 plus 3 over x minus 5 times x plus 5 minus 2x over x minus 1 times x minus 5 equal to 0. And so I like to build up the common denominator, which in this case, the LCD is x minus 1 times x minus 5 times x plus 5. All right, so our first fraction there, x over x minus 1 times x plus 5, has already 2 of the factors. So we need to multiply top and bottom by the third factor, which would be x plus 5. Let me just actually do that in the next step here. So that would be x times x minus 5 all over x minus 1 times x plus 5. All right, plus 3 over, well, that second fraction there, it's missing the x minus 1 factor in the denominator, so we'll multiply top and bottom of that by x minus 1. Oops, I forgot to write this term here. So we have x minus 1 times x minus 5 times x plus 5. And the second fraction, we have x minus 1 and x minus 5, but we don't have the x plus 5, so we multiply top and bottom by x plus 5. Top and bottom. Okay, so then what you do next is multiply through by the LCD, which basically leaves the numerator. So I like to say forget about the denominators and just write the numerators. Okay, but I'm going to actually distribute here. And so here we would get x squared minus 5x. Here we get 3x minus 3. And here we get 2x squared plus 10x. Okay, so then now our next line would simply be just x squared minus 5x plus 3x minus 3 minus this minus sign here. I'm going to actually distribute it to the numerator to the numerator to get negative 2x squared and then minus 10x, and this is all equal to 0. Now let's combine our like terms. So we have x squared minus 2x, and so that's going to give us negative x squared. We have a negative 5x and a 3x and a negative 10x. So that's going to give us negative 12x. And then we have a sole constant there of negative 3. So minus 3 equals 0. All right, I like to have a positive coefficient here, so I'm going to multiply through by negative 1 to rewrite this as x squared plus 12x plus 3. And this quadratic function here, or expression, cannot be factored over the integers or whole numbers here. And so we are going to go ahead and use the quadratic formula. All right, so I need to find those zeros, right? X is equal to minus b plus or minus square root of 4, or b squared minus 4 times a times c all over 2a. Okay, so we could see that our a is 1, our b is 12, and our 3 is c. Okay, so we have minus 12 plus or minus the square root of b squared, which is 12 squared, minus 4 times a, which is 1, times c, which is 3, all over 2 times 1. Okay, so now we have negative 12 plus or minus, well, that's going to give us what? 12 squared, 144, minus 12 over 2. All right, so that's going to give us negative 12 plus or minus the square root of 132 all over 2. And I believe square root of 132, well, it's 4 times something. Let's see, what is it? 4 times 32. Anyways, let's reduce that 12 plus or minus. I know there's a 4 in there because 132 is, in factorization of it, I know it goes in 4 times. 4 times what? Let's see. Times 33, actually. 4 times 33. That's what it is. So that's the perfect square. So we could rewrite that one square root of 132 as 2 times 33. All over 2. All right, so you can see that 2's in common in the numerator and the bottom. So we get negative 6 plus or minus the square root of 32. So we have 2 zeros here. X equal to negative 6 minus root 33. And I'm going to get an approximation of this, which is about negative 11.745 rounded to 3 decimal places. And x equals negative 6 plus radical 33. And a decimal approximation of that would be negative 0.255. Okay. So now we have found our critical values. The critical values for this related rational equation or related rational expression are the values negative 6 minus root 33, negative 6 plus root 33. We also had negative 5. And we also had, what was the other ones? I forgot. Negative 5, positive 5, and 1. So those are the critical values. All right, so this is going to break up our number line into these numbers here. So the first critical value would be -6 minus root 33, then followed by -5, and then followed by -6 plus root 33. Once again, using decimal approximation to get the idea where those numbers are relative to each other. And then +1, and then +5. So we have several intervals here. Okay, so we know that the zeros occur at those critical values at -6 minus root 33 and -6 plus root 33 will make the rational expression 0 because they're the zeros. But the other guys will make the function undefined. Okay, so we can see we have one interval going from -infinity to -6 minus root 33. The next interval is between -6 negative root 33 minus root 33 and -5, and then between -5 and -6 plus root 33, and then between -6 plus root 33 to 1, and then between 1 and 5, and then between 5 and infinity. Okay, so now what we do is take a test point. So I'm going to take, say, something away from -6 root 3. I chose -20, and then I chose -8 between those two, and then -2, and then 0, and then between 1 and 5, I chose 2, and after something bigger than 5, I chose 8. Okay, so those are my test values: -20, -8, -2, 0, and 2, and 8. And so then the next step to do is plug in those values into the rational expression or the rational function. And I already did these calculations, but our -20 is 163 over 7,875. So it's very close to 0. It's approximately 0.021 rounded to 3 decimal places. So we'll note that it's positive there. All right, now I'm plugging in our rational -8 into our rational function. Once we get the fraction -29 over 351, which is roughly -0.083. Okay, once again, these calculations are very tedious by hand, so I already did it in advance. All right, so the rational function evaluated at -2 is 17 over 63, which is roughly 0.270 if I round to 3 decimal places. Okay, by the way, so this is negative between -6 minus root 33 and -5, and it's positive between -5 and -6 plus root 33. Okay, now we take our next test value of our r of 0, excuse me. And so we could see that we get 17 over 63, which is roughly, sorry, I screwed up, messed up there. This is R0 would be -3 over 25, which is equal to -0.12. All right, and the next one, so that means it's negative between -6 plus root 33 and 1. And then now the rational function evaluated at 2. So that would give us 31 over 21, which is about 1.476 roughly. And so that's positive. And then the rational expression or function evaluated at 8 would give us -163 over 273, which is roughly -0.597. So it's negative on that interval there from 5 to infinity. All right, so the original rational expression that we were interested in, it's a lot of work there, when it was less than 0. And that will imply, and I'm just gonna cheat here. Let me copy this real quick instead of writing it all down again. would imply the solution sets for that try to delete that there. Would imply in other words, the related rational function inequality, the solution set of that would also be the same as the solution set of the original inequality, x over x squared plus 4x minus 5 plus 3 over x squared minus 25 less than 2x over x squared minus 6x plus 5. So we just need to solve this here, which means less than 0. And so less than 0 means we're looking for where the rational function has outputs that are negative. So looking at our little chart here, there is a couple regions where that happens, right? Between here and here. So between -6 and -5, and between -6 plus root 33, and between 5 to positive infinity. Okay, so then our solution set then would be, and we don't want it to be 0, so we would not include our 0. So it would be, the solution set would be -6. By the way, I forgot to highlight that over there. Okay, so -6 minus root 33, comma, to -5. And union -6 plus root 33, comma, to 1, parenthesis, union, parenthesis, 5 to positive infinity. So any value in that interval there, that union of intervals there, is a solution to both of these inequalities. Okay, since those inequalities are equivalent. All right, lastly, let's see how we can get the same result roughly, or exactly. I mean, it's harder to see because of the irrational zeros, but let's see how we could use Desmos to get the same solution set. All right, so here's Desmos. I'm gonna go ahead and click on the graphing calculator. We're gonna have to open this just a tad little wider. All right, so my function r of x is equal to, and the first fraction that we originally defined was x squared plus 4x minus 5 plus 3 all over x squared minus 25, and then minus 2x over x squared minus 6x plus 5. Okay, so let's make that a little bit wider there. All right, so there's our rational function. And you could, so we're interested in when this is less than 0. You can see we would have an asymptote here at x equal to 1 or -5. Also at x equal to 1. In fact, let me just go ahead and do that. X equal to -5. So it's visible. X equal to 1, and also x equal to 5. And then let me dot it, so, and then make them the same color. So dot, all right. All right, so it looks like I got it there, and those are our asymptotes. Okay, so now that we have our asymptotes there, let's go ahead and see where this function is less than 0. So that means it would have to be below the y-axis. In other words, we want the outputs that give us negative values. Okay, so I'm going to zoom out just a tad here and kind of examine this. Well, we know we have a 0 just algebraically, but it's hard to see here. It's very close. So you see that it's very close to the x-axis because it's going to be a horizontal asymptote. But we know there's a 0 there, roughly around, from our estimations of the zeros, we probably have one around on -11, right? We saw it, so it's going to be somewhere there. There it is, right there. So about a -11 0.744. You can't even see that it goes up, but if you zoom in close enough, you can make it out. Where is it at? There it is. You can make it out. Zoom in just a tad. You can kind of see that, okay, it's starting, you can barely see, you can start seeing that it's above the x-axis. It's very close to the x-axis. But if you zoom out, then eventually once it passes the R0 here, it starts getting closer, or starts going below the x-axis. So we know to the right of that 0 there, of -6 minus root 33, it's going to be below the x-axis. And then let me go ahead and zoom back out. So it's coming this way, and then still going to continue below because it's approaching that asymptote. So as you approach that asymptote of x equal to -5, from the left, you see it's going to shoot down. So this part of the graph from the 0 to there, which would be -6 minus root 3 to x equal to -5, the graph is entirely below the x-axis. So that would be the one solution set or interval. And then you could see here at our other 0, which was root 6 plus, -6 plus root 33, and then to the next asymptote, which happened at x equal to 1. You can see that the graph is entirely below the x-axis, which means it gives us negative outputs, negative y values. Okay, and in between those two asymptotes, you see the graph's entirely to above, so therefore it's not that. And then you can see from the asymptote here, from 5 to infinity, the graph is entirely below the x-axis because we have no more zeros. But it's kind of hard to see that unless you go there. It's going to get very arbitrary close to the x-axis. So you see that it does. It's an asymptote, but we wouldn't really guarantee that it doesn't cross way down there unless we kind of examine it a little bit closer. But that's how you would use the graph to solve that inequality, which once again, you're looking for where it's below the x-axis, and you can see that there's 3 intervals where this would happen. That's it for this video.